To understand why heat flows, you first have to understand that heat does not exist, not in the way you think it does. You view heat as a tangible quality, an essence that radiates from a fire or rises from pavement. But if we descend to the atomic scale, that quality dissolves. There is only motion, kinetic energy. This is the first uncomfortable truth. Hot is just a word for fast-moving particles. Cold is a word for slow-moving ones. When you touch a hot stove, you are not absorbing a substance. Your skin is being bombarded by billions of vibrating iron atoms, hammering against the molecules of your hand, transferring their chaotic momentum into your flesh. Now, imagine we filmed this process with a high-speed camera, not at the human scale, but at the scale of a single collision between two atoms. Atom A is hot, moving fast. Atom B is cold, moving slowly. They collide, and the chaos energy is exchanged. Now, play that film backward. In the rewound version, the atoms bounce off each other and separate. If you showed this backward clip to a physicist, could they tell you it was fake? Could they point to a law of motion and say, that is impossible? No. This is the reversible nightmare. The laws of mechanics, Newton's laws, which govern these collisions, are completely symmetrical in time. They work exactly the same way forward as they do backward. There is nothing in the equation $F equals ma dollar that distinguishes yesterday from tomorrow. If you watch a single collision, you cannot tell if time is moving forward or backward. Both scenarios are perfectly valid solutions to the equations of physics. Now, zoom out. Your cup of coffee is just a collection of these collisions, trillions upon trillions of them. If every single individual collision is reversible, if every single interaction allows for energy to move from slow to fast just as easily as fast to slow, then the anti-ray system should be reversible. The logic is inescapable. If the fundamental laws of the universe do not care about the direction of time, why does your coffee always cool down? Why does the heat never spontaneously rush back into the cup from the surrounding air? The air molecules in your room have plenty of energy. There is no force field stopping them from coordinating their impacts, striking the coffee surface, and transferring all their energy back into the liquid, making it boil while the room freezes. According to the strict laws of motion, this event is physically possible. It violates no fundamental force. It breaks no conservation law. Yet, you have never seen it happen. You are living in a universe where the underlying rules permit things to happen in reverse. But the reality you experience is locked in a one-way street. The microscopic world is reversible, the macroscopic world is not. Something is missing. There is a bridge we haven't crossed. The answer isn't in the physics of the atoms themselves. It is in the distinction between what we see and what is actually happening. To find the bridge between the reversible atom and the one-way coffee cup, we have to address a human bias. You look at a neat pile of sand and call it ordered. You look at a scattered pile of sand and call it disordered. You think nature shares this opinion. It doesn't. To an atom, there is no such thing as a mess. Every single possible arrangement of particles is just as unique and just as meaningless as any other. If you have 10 coins and they all show heads, you think that's special. If they show a random sequence of heads and tails, you think that's random. But for the coins, the specific sequence of HTTLHTLLHH is exactly as difficult to achieve as 10 heads in a row. It is a 1 in 1,000 outcome. This brings us to Feynman's core distinction, the difference between the macro state, what you see, and the micro state, what is actually happening. The macro state is the big picture. It's the temperature of the coffee, the pressure in a balloon, or the fact that the milk is stirred into the tea. The microstate is the exact position and velocity of every single molecule in that system. Here is the discomfort. Nature only operates at the level of the microstate. It just moves things around according to the laws of motion we discussed in Chapter 1. It doesn't know it's stirring the milk. It doesn't know it's cooling the coffee. It is simply jumping from one microscopic arrangement to another. You perceive heat flow because you are blind to the microstate. You cannot see the individual molecules. You only see the macrostate, the average. Imagine two rooms connected by a door. One room is full of fast atoms, hot. The other full of slow atoms, cold. When you open the door, they mix. After a while, both rooms have a medium temperature. To you, this looks like heat flow. To you, the system has moved from an ordered state separated to a disordered state mixed. But ask yourself, what changed flow? Are the atoms? Nothing. They are still just bouncing. If you were to take a snapshot of the mixed room, the specific arrangement of atoms you see in that instant is just as rare as the arrangement where they were perfectly separated. Every single microscopic configuration is equally likely, or, more accurately, equally unlikely. So why does the mixed state always win? It's not because the atoms prefer it. It's not because there is a force of mixing. It's because your human definition of mixed covers trillions upon trillions of different microscopic arrangements, while your definition of separated only covers a few. You have been tricked by your own senses. You think you are watching a physical process called flow. In reality, you are just watching a system wander blindly through a desert of possibilities. We have removed the idea that nature has a preference. We are left with something much more mechanical and, in a way, much more hollow. Heat doesn't flow because it wants to reach equilibrium. It flows because equilibrium is a massive, bloated category that is almost impossible to avoid. Now we reach the heart of Feynman's logic. If nature doesn't care about order, and every microscopic arrangement is equally likely, then why does the universe seem to have a direction? The answer is found in the simple act of counting. Imagine you have a box containing only 4 atoms. Let's say 2 are hot fast and 2 are cold slow. You divide the box with a conceptual line down the middle. How many ways can you arrange these 4 atoms so that all the hot ones are on the left and all the cold ones are on the right? Exactly 1 way. Now, how many ways can you arrange them so that the energy is mixed with 1 hot and 1 cold atom on each side? If you sit down and do the math, you'll find there are 6 different ways to achieve this mixed macro state, even with only 4 particles. The mixed state is 6 times more likely than the separated state, simply because there are more ways to be mixed. If the atoms are just bouncing around randomly, jumping from one arrangement to another, you will spend 600% more of your time looking at a lukewarm box than a separated box. But 4 atoms is not a cup of coffee. A standard cup of coffee contains roughly 1,025 dollar molecules. That is a 1 followed by 25 zeros. When you deal with numbers this large, the game of numbers stops being a game and becomes a mathematical prison. If you have 1 trillion atoms on the left and 1 trillion on the right, the number of ways to have them mixed doesn't just outnumber the separated ways by 6 to 1. It outnumbers them by a factor so large that the human mind literally cannot conceptualize it. It is a ratio larger than the number of atoms in the observable universe. This is why heat flows. When you put a hot spoon into cold water, the atoms start colliding. They are essentially shuffling a deck of cards. The hot spoon, cold water state is like a deck of cards perfectly sorted by suit. As the atoms bounce, the deck gets shuffled. Does the shuffling force the cards to be mixed? No. There is no shuffling force that hates order. It's just that there are billions of ways for a deck to be messy, and only 1 way for it to be sorted. As the shuffling continues, you are simply overwhelmed by the sheer volume of messy possibilities. You move toward equilibrium not because you are being pushed, but because you are wandering into the largest room in the house. Feynman points out that if you wait long enough, the deck could theoretically unshuffle itself. The atoms in the water could all happen to strike the spoon in such a way that the spoon becomes red hot and the water freezes. The math says it will happen. But the math also says you would have to wait trillions of times longer than the current age of the universe to see it. You think you are seeing a law of physics. You are actually just seeing a very, very, very stable coincidence. Heat flows because the alternative is so statistically lonely that it might as well not exist. You might find it easy to accept that a deck of cards stays shuffled. 52 cards is a manageable number, but your intuition likely rebels at the idea that the entire world, your car, your house, your body is governed by the same luck. You feel there must be a firmer hand on the wheel. This is the tyranny of scale. In a small system, the laws of thermodynamics are broken constantly. If you look at a microscopic volume containing only 5 molecules of gas, it is actually quite common to see them all move to one side, or all momentarily stop moving. In that tiny world, the arrow of time is broken. Heat flows backward. Entropy decreases. Order emerges from nothing. But as you add particles, the probability of these fluctuations doesn't just drop linearly, it collapses exponentially. If you flip a coin 10 times, getting 10 heads is rare, about 1 in 1,000, but you might see it happen in an afternoon of trying. If you flip a coin 100 times, the odds of all heads drop to 1 in a non-alien. You could flip coins for the entire history of the Earth and never see it once. Now consider the $1,023 particles in a gram of matter. The reason you have never seen a cold cup of coffee spontaneously boil is not because it is forbidden. It is because the unshuffling requires a level of coordination that the universe simply cannot provide to make the coffee hot. Every single one of those septillions of particles would have to accidentally choose the exact same direction and timing for their collisions. It is a conspiracy of such vast proportions that the word impossible becomes a functional truth, even if it is a mathematical lie. Feynman's point is that we have mistaken absolute improbability for physical law. We see a wall where there is actually just a very, very steep hill. This realization should make you feel precarious. It means that the laws you rely on, the fact that your floor stays solid, that the air in your room doesn't suddenly retreat into a corner and leave you to suffocate, are not enforced by a cosmic police officer. They are held up by nothing more than the fact that there are a lot of atoms, and they are all very busy being disorganized. The law of heat flow is just the law of large numbers dressed up in a lab coat. If you were small enough, or if the universe were empty enough, the law would vanish. You are only a prisoner of thermodynamics because you are too large to see the chaos. If the flow of heat is just a movement from the unlikely to the likely, then we have to reconsider everything we know about time. You feel time passing. You remember the past, but you do not remember the future. You see eggs break, but you never see them unbreak. You attribute this to a fundamental property of the universe, a forward gear in the engine of reality. But Feynman's statistical reality suggests something far more haunting. The only reason past and future look different to you is because of the direction of heat flow. And as we have established, heat flow is just the process of a system becoming more probable. This means the past is not a place you came from. The past is simply a name we give to a state of lower entropy. Think about your brain. To form a memory, your neurons must undergo a physical change. That change requires energy. That energy dissipation creates a tiny bit of heat, a tiny bit of shuffling in the deck of the universe. You can only remember in the direction of increasing probability. If the universe were at a state of maximum probability, if every deck were perfectly shuffled and every room were a uniform temperature, time would not stop, but it would become meaningless. There would be no changes in the macro state for you to track. There would be no gradient to slide down. This leads to a chilling conclusion. We only exist because we are currently sliding down a slope of improbability. You think of the normal state of the universe as the one you see outside your window: stars, planets, life, organized structures. But according to the numbers, that is not normal at all. The most likely state for the universe is a cold, gray, uniform smear of radiation. We are a fluctuation. We are like a deck of cards that, by some staggering fluke, was found halfway through a shuffle, still showing streaks of the original suits. We call those streaks history. We call the fading of those streaks time. You aren't moving through time. You are part of a massive, cosmic accident that is slowly correcting itself. The heat flowing out of your body and into the cold air isn't just physics, it is the universe's way of erasing the weird, unlikely you and returning to the vast, comfortable silence of the probable. The arrow of time is not a property of space. It is a symptom of a lopsided beginning. We are left with a final, staggering problem. If the universe is just a deck of cards being shuffled into a mess, and if heat flows only because the messy state is so much more likely than the ordered one, then why was the deck ever sorted in the first place? If you walk into a room and see 1,000 coins on the floor all showing heads, you don't marvel at the law of coin heads. You immediately ask, who put them like that? This is the ultimate consequence of Feynman's simple answer. By explaining why heat flows toward disorder, he forces us to confront the fact that our entire existence depends on a beginning that was impossibly, terrifyingly ordered. For heat to flow for 13.8 billion years, the universe had to start in a state of such low entropy, such high concentration, and such profound unlikelihood that it defies any statistical explanation. We find ourselves in a cosmic once upon a time. The Big Bang was not just an explosion, it was the ultimate sorted deck. Everything we see, the formation of galaxies, the burning of stars, the evolution of DNA. The thoughts occurring in your brain right now is just a byproduct of that original concentrated unlikeliness slowly spreading out. We are living in the wake of a miracle of probability. Feynman's perspective strips away the comfort of fundamental laws and replaces it with the law of the accidental. You are not a creature of law. You are a localized eddy in a vast, outgoing tide of energy. The heat flowing from your coffee, the sun warming your skin, and the aging of your own cells are all the same event. The universe finally, slowly, finding its way into the most probable state. The simple answer is that things happen because they are likely, but the simple answer leaves us with a haunting silence. It means that order is not the goal of the universe. It is a decaying relic. One day, the shuffling will be complete. The last temperature difference will vanish. The final bit of order will be smeared into the gray background of equilibrium. There will be no more hot, no more cold, and therefore, no more time. Until then, you exist in the middle of a grand, statistical dissipation. You are a brief, beautiful flicker of no in a universe that is steadily, mathematically, saying yes to the dark. Reality isn't governed by a master plan. It's just that, eventually, every deck of cards finds its mess. And we are the lucky few who get to watch the shuffle.